Tonight, we're going to explore something you think you understand, but probably don't. Gravity. You've felt it every second of your life. It keeps your feet on the ground and the earth circling the sun. It seems so simple, so obvious. But here's what most people don't realize. Gravity is the deepest mystery in all of physics. We've known about it longer than any other fundamental force. Newton figured out how it works over 300 years ago. Einstein revolutionized our understanding a century ago. And yet, to this day, we still don't know what gravity actually is. It doesn't fit with our other theories. It behaves strangely at quantum scales. And by the end of this journey, you'll understand why solving gravity might be the key to understanding reality itself. Before we dive into this cosmic mystery, if you find yourself fascinated by questions about the fundamental nature of reality, a quick like or subscribe really helps support this channel. It's a small thing, but it means a lot to me. Now, let's begin. Let's start with something you've never thought twice about. Right now, wherever you are, an invisible force is pulling you toward the center of the Earth. It's been doing this every second of your life. It never stops, never weakens, never takes a break. When you were born, it was there. When you took your first steps, you were fighting against it. When you threw a ball as a child and watched it arc back to the ground, you were watching it in action. This is gravity. And it seems so completely ordinary, so woven into the fabric of everyday experience, that asking what it actually is might seem like a strange question. Gravity is just gravity. Things fall. The earth pulls. What more is there to say? But here's what makes gravity so fascinating and ultimately so troubling for physicists. It's the most familiar force in the universe, the one we've felt since before we could walk or talk or understand anything at all. And yet, after more than 300 years of studying it, after Newton and Einstein and countless brilliant minds have wrestled with its secrets, we still don't completely understand what it is. Not how it behaves. We know that extraordinarily well, but what it actually is at the deepest level, why it exists, how it really works, these questions remain open. And that's remarkable when you think about it. The first force humans ever noticed is the last one we'll fully comprehend. Let's go back to the beginning, before Newton, before anyone had any scientific understanding of why things fall. For most of human history, gravity wasn't even a concept. People knew things fell when you dropped them. Of course, that was obvious. But they explained it in ways that seem almost comical to us now. Aristotle, the Greek philosopher who lived around 350 years before the Common Era, had an explanation. He believed that all matter was made of 4 elements: earth, water, air, and fire. Each element had a natural place in the cosmos. Fire and air naturally rose upward. Earth and water naturally sank downward. When you dropped a rock, it fell because the rock was made mostly of the earth element, and the earth element wanted to return to its natural place at the center of the universe. This theory seems absurd today, but it was the dominant explanation for why things fall for nearly 2,000 years. That's longer than the entire span from the Roman Empire to the present day. For all that time, the best minds in the Western world believed that objects fell because they were seeking their natural home. Aristotle also believed that heavier objects fell faster than lighter ones. This seems intuitive. Drop a bowling ball and a feather, and the bowling ball hits the ground first. But the reason isn't because heavy things fall faster. It's because air resistance slows the feather more than the bowling ball. In a vacuum, they fall at exactly the same rate. Galileo demonstrated something like this in the late 1500s, dropping objects from the Leaning Tower of Pisa, though the famous story may be somewhat legendary. The definitive proof came when Apollo 15 astronaut David Scott dropped a hammer and a feather on the moon, where there's no air, and they hit the ground at the same instant. But back in ancient times, No one understood this. Aristotle's physics dominated. The ancient Greeks also noticed something peculiar. While objects on Earth fell downward, the celestial objects didn't seem to follow the same rules. The moon didn't fall to Earth. The sun didn't fall. The planets moved through the sky in regular patterns, some of them quite complex, but they didn't crash down. The Greeks concluded that the heavens must operate under different laws than the Earth. This made a kind of sense to them. The Earth was a place of change, decay, and imperfection. The heavens were eternal, perfect, and divine. It seemed natural that they would follow different physics. The celestial realm was governed by circles and crystalline spheres. The terrestrial realm was governed by the four elements seeking their natural places. This division between heavenly physics and earthly physics persisted for centuries. The idea that the same laws might govern both a falling apple and the orbiting moon would have seemed absurd, even heretical. The heavens were sacred. The earth was mundane. How could they possibly follow the same rules? And then came Newton. Isaac Newton was born on Christmas Day in 1642 in Woolsthorpe, England. He was a premature baby, so small he could reportedly fit in a quart pot. His father had died 3 months before his birth. His mother remarried when he was 3 and left him with his grandmother. By all accounts, Newton had a difficult childhood and remained emotionally distant and quarrelsome throughout his life. He was also one of the greatest geniuses in human history. In 1665, when Newton was 22, the Great Plague swept through England. Cambridge University, where Newton was a student, closed its doors to prevent the spread of disease. Newton retreated to his family's farm in Woolsthorpe. And there, during what would become known as his Year of Wonders, he made discoveries that would change the course of science. You've probably heard the story of the apple. Newton sitting in his garden, an apple falling from a tree, and suddenly the secrets of gravity becoming clear. The popular image shows Newton being bonked on the head by the apple, which almost certainly never happened. But he did observe apples falling. And he did ask a question that no one had asked quite so clearly before. Why does the apple fall straight down? Why toward the center of the earth? These seem like trivial questions. Things fall down because down is where the ground is. But Newton pushed further. What if the same force that pulls the apple also pulls the moon? This was revolutionary. Remember, for 2,000 years, learned people had believed that the heavens and the earth followed entirely different laws. The moon was a celestial object, part of the eternal realm of perfect circles and crystalline spheres. The apple was an earthly object, made of elements seeking their natural place. The idea that they might both be responding to the same force would have struck Aristotle as nonsense. But Newton considered it seriously. And when he worked out the mathematics, something beautiful emerged. The moon, Newton realized, is falling toward Earth, just like the apple. But unlike the apple, the moon is also moving sideways. It's moving so fast sideways that as it falls, it keeps missing the Earth. The Earth's surface curves away beneath the falling moon at the same rate that the moon falls toward it. The result is not a crash, but a continuous curve, a circle, an orbit. The moon is falling around the Earth. That's what an orbit is. Continuous falling without ever hitting the ground, because you're moving sideways fast enough that the ground keeps curving away beneath you. Think about that for a moment. Every satellite orbiting Earth, every planet orbiting the sun, every star orbiting the center of its galaxy is falling endlessly, but moving sideways fast enough to keep missing what it's falling toward. Orbits are not mysterious exceptions to gravity. They're gravity in action, combined with sideways motion. Newton didn't stop with the moon. If the same force pulls apples and moons, maybe it pulls everything. Maybe every object in the universe attracts every other object with the same kind of force. He formulated this insight into what we now call the law of universal gravitation, and the mathematics he developed to describe it remains in use today, more than 300 years later. The law says this: every particle of matter in the universe attracts every other particle with a force. This force is proportional to the product of their masses and inversely proportional to the square of the distance between them. Let me unpack that, because it's elegant and important. First, the force depends on mass. More massive objects attract more strongly. The Earth pulls on you with a noticeable force because the Earth is massive, about 6 trillion kilograms. You pull on the Earth too, with exactly the same force but in the opposite direction. But because you're so much less massive than the Earth, you move and it doesn't, at least not perceptibly. Second, and this is crucial, the force decreases with the square of the distance. Double the distance between two objects, and the gravitational force between them becomes not half as strong but 1/4 as strong. Triple the distance, and it becomes 1/9 as strong. This is what mathematicians call an inverse square relationship. Why the square? It has to do with geometry, with how things spread out in three-dimensional space. Imagine gravity radiating outward from an object like light from a lamp. As it spreads, it covers a larger and larger sphere. The surface area of a sphere increases with the square of its radius. So the same amount of gravity, spread over a sphere twice as large, is spread over 4 times the area. The intensity at any point is 1/4 as strong. This inverse square law appears throughout physics. It governs light intensity, sound intensity, and electromagnetism. There's something fundamental about it, something connected to the geometry of the three-dimensional space we live in. Newton published his gravitational theory in 1687 in a book called Philosophia Naturalis Principia Mathematica, usually just called the Principia. It's one of the most important scientific works ever written. In it, Newton laid out his laws of motion and his theory of universal gravitation. He showed how these principles could explain phenomena that had puzzled humanity for millennia. Why do planets orbit the sun in ellipses, as Kepler had discovered decades earlier? Newton's equations explained it. Why do the tides rise and fall? Newton explained that too. It's the moon's gravity pulling on Earth's oceans, combined with the sun's gravity, creating bulges in the water that we experience as high and low tides. Why does Earth bulge slightly at its equator? Newton's equations predicted this before it was measured. The spinning Earth flings material outward at the equator, and gravity shapes the result into an oblate spheroid rather than a perfect sphere. Newton could calculate the orbits of comets, those mysterious visitors that ancient people thought were omens or signs from the gods. He could predict when they would return. Halley's Comet, named after Newton's friend Edmund Halley, returns every 75 to 79 years, just as Newton's equations predict. It was last visible in 1986. It will return in 2061. The predictive power of Newton's gravity was unprecedented. For the first time, humans could calculate the future positions of celestial objects with precision. We could predict eclipses, the return of comets, the motions of planets. We had cracked a code that the universe seemed to be written in. The heavens were not mysterious or divine, they were mathematical. Consider the discovery of Neptune, which stands as one of the greatest triumphs of Newtonian gravity. By the early 1800s, astronomers had been tracking the planet Uranus for decades. Uranus was discovered in 1781 by William Herschel, and astronomers quickly calculated its orbit using Newton's equations. But there was a problem. Uranus wasn't quite where it should be. Its actual position kept drifting slightly from the predicted position. Some astronomers wondered if Newton's theory was breaking down at such great distances, but others had a different idea. What if there was another planet, one that hadn't been discovered yet, whose gravity was tugging on Uranus and perturbing its orbit? In the 1840s, 2 mathematicians independently took up this challenge. In France, Urbain Le Verrier calculated where this hypothetical planet must be based on the size and direction of Uranus's deviations from its predicted orbit. In England, John Couch Adams did the same calculation. Their predictions were remarkably similar. And in September 1846, German astronomer Johann Gaillet pointed his telescope at the coordinates Le Verrier had specified. There, within 1 degree of the predicted position, was Neptune. Think about what happened here. Mathematicians, using nothing but Newton's equations and observations of Uranus's position, calculated where an unseen planet must be. Astronomers pointed their telescopes at that spot, and there it was. Newton's theory didn't just describe gravity, it discovered new worlds. The scientific and philosophical implications were profound. If mathematics could reveal the existence of objects before they were seen, then the universe was truly law-governed in a way the ancients had never imagined. Newton's equations weren't just convenient calculation tools. They seemed to describe something deep about how reality worked. But for all its triumphs, Newton's gravity had a problem that Newton himself recognized. He could tell you how gravity behaved with exquisite precision, but he couldn't tell you what it was. In 1693, Newton wrote to his colleague Richard Bentley about this very issue. He said the idea that one body could act on another across empty space without any medium to carry the force was so absurd that no philosophical mind should accept it. And yet, that's exactly what his equations assumed. Gravity seemed to act instantaneously across any distance. The Sun is 93 million miles from Earth. Light takes about 8 minutes to travel that distance. But in Newton's equations, if the Sun suddenly moved, Earth would feel the change in gravitational pull immediately, with no delay. How could that be? What was carrying the force across that vast empty space? What was the mechanism? Newton had no answer. He famously wrote, "I have not as yet been able to discover the reason for these properties of gravity from phenomena, and I do not feign hypotheses." In other words, I can tell you how gravity works. I can give you equations that predict its effects with stunning accuracy, but I cannot tell you what gravity actually is. I cannot tell you why it exists or what carries it through space, and I'm not going to make something up to cover my ignorance. This humility is striking. Newton had achieved one of the greatest scientific breakthroughs in history. He had unified the physics of Earth and the heavens. He had given humanity power to predict the motions of planets and the falls of apples with the same equations. But he was honest about what he didn't know, and for more than 200 years after Newton, that was fine. Scientists used his equations without understanding the underlying mechanism. Because the equations worked so well, why worry about what gravity really is if you can calculate its effects accurately? Physics became, for many practitioners, a practical discipline of prediction rather than a philosophical quest for ultimate understanding. But those nagging problems didn't go away. There was the instantaneous action at a distance. Nothing else in physics worked that way. Light took time to travel. Sound took time. Even when you push something, the push took time to propagate through the material. But gravity, supposedly, acted instantly across any distance. This seemed deeply wrong, and there was a small but persistent discrepancy in the orbit of Mercury. Mercury, the planet closest to the Sun, has an orbit that slowly rotates over time. The point where Mercury comes closest to the Sun, called perihelion, shifts around slightly with each orbit, tracing out a pattern like a spirograph flower over centuries. This is called precession. Newton's equations could explain most of this precession. The gravitational pulls from Venus, Earth, and other planets tug on Mercury and cause its orbit to rotate. But when astronomers added up all these effects, they came up short. Mercury's perihelion precessed about 43 arcseconds per century, more than Newton's theory could account for. 43 arcseconds is a tiny amount. It's about 1/100th of a degree per century, but it was measurable, and it was real, and it couldn't be explained. Some astronomers proposed an undiscovered planet, which they named Vulcan, orbiting even closer to the Sun than Mercury and causing the extra precession. Telescopes searched for Vulcan during solar eclipses, when a small planet near the Sun might be visible. Reports of sightings came in occasionally, but none could be confirmed. Vulcan didn't exist. The problem wasn't a missing planet. The problem was that Newton's theory, for all its successes, wasn't quite right. It was incredibly accurate. Accurate enough to discover Neptune, accurate enough to send spacecraft to distant worlds. But in the extreme conditions near the Sun, in the intense gravitational field that Mercury experiences, Newton's equations gave an answer that was ever so slightly wrong. This tiny discrepancy would eventually lead to a complete revolution in our understanding of gravity. But before we get there, let's appreciate something about Newton's picture that is often overlooked. In Newton's framework, space is an empty stage. It's a fixed, unchanging arena in which objects exist and move. Space has 3 dimensions. Objects have positions in this space, and those positions can change over time. But space itself doesn't do anything. It doesn't bend, stretch, or respond to the objects within it. It's just there, eternal and unchanging, a backdrop for the drama of physics. Time, similarly, is a universal metronome. It ticks away at the same rate everywhere, for everyone. A second on Earth is the same as a second on the Moon, or a second in a distant galaxy. Time flows uniformly, inexorably, and the same for all observers. Gravity, in this picture, is a force that somehow reaches across the empty stage of space to pull objects toward each other. How it reaches across that stage, Newton couldn't say, but he could describe exactly how strong the pull would be at any given distance. This picture is intuitive. It matches our everyday experience. Space seems like an empty container. Time seems to flow the same everywhere. Gravity seems to pull things down. We've built bridges, launched rockets, and designed satellites using Newton's framework. But it's not the last word. The problems Newton identified, the action at a distance, the inability to explain the mechanism, these were hints that the picture was incomplete. The tiny error in Mercury's orbit was another hint. And when Einstein came along, he wouldn't just patch up Newton's theory. He would replace its entire conceptual foundation with something radically different. Before we get there, let's appreciate one more puzzling aspect of gravity that Newton's framework highlights. Even if it can't explain it, gravity is incredibly weak. This might seem counterintuitive. After all, gravity holds you to the Earth. It keeps the Moon in orbit. It holds galaxies together. How can something so obviously important be weak? Consider this experiment. Take a small refrigerator magnet and use it to pick up a paperclip from a table. You've just demonstrated that the electromagnetic force from that tiny magnet is stronger than the gravitational pull of the entire Earth on the paperclip. The entire planet, 6 trillion kilograms of rock and iron and magma, is pulling down on that paperclip. And a magnet you could hold between 2 fingers is overcoming that pull. If you do the mathematics and compare the electromagnetic force between 2 protons to the gravitational force between them, you find that electromagnetism is stronger by a factor of about 10 to the 36th power. That's a 1 followed by 36 zeros. The strong nuclear force, which holds atomic nuclei together, is even stronger. Gravity is weak, spectacularly, bizarrely weak compared to the other fundamental forces. We only notice it at all because we happen to live on a planet with an enormous amount of mass, all of it pulling in the same direction. Even then, a small child can overcome Earth's gravity by jumping into the air. At least for a moment. Why is gravity so much weaker than the other forces? We don't know. It's one of the deep mysteries of physics, and we'll return to it later. But for now, Just note that Newton's framework describes this weakness without explaining it. Gravity follows the inverse square law, just like electromagnetism. But the constant of proportionality, the number that determines how strong the pull is for a given mass at a given distance, is incredibly tiny compared to the corresponding constants for other forces. Newton gave us the how of gravity. He gave us equations that work, that predict, that allowed humanity to reach the moon and send probes to the outer planets. But he explicitly admitted that he didn't know the why. He didn't know what gravity was, only how it behaved. This distinction between description and explanation is fundamental to science. A good scientific theory describes patterns in nature and makes accurate predictions. But a truly deep theory also explains why those patterns exist. Newton achieved the first without the second. And so, for more than 2 centuries after the Principia, physicists and astronomers used Newton's equations with great success while puzzling over what gravity really was. Some proposed that space was filled with an invisible medium, an ether, that carried gravitational influences the way air carries sound. But no one could detect this ether, and no one could explain how it worked. The puzzle of gravity, the most obvious and familiar force, remained stubbornly unsolved. We could calculate its effects with remarkable precision. We could use it to navigate spacecraft across the solar system, but we couldn't say what it was. Then, in the early 20th century, a new way of thinking emerged. It came from a patent clerk in Switzerland who had been thinking about what would happen if you chased a beam of light. His name was Albert Einstein, and he was about to show that Newton's beautiful picture of fixed space and universal time was fundamentally wrong. Gravity wasn't what Newton thought it was. Space wasn't what Newton thought it was. Time wasn't what Newton thought it was. And the deepest mysteries of gravity were about to get even deeper. Newton's theory of gravity reigned supreme for more than 2 centuries. It predicted eclipses. It discovered new planets. It sent our minds, if not yet our machines, into the heavens with mathematical precision. But those nagging problems, the mysterious action at a distance, the tiny error in Mercury's orbit, never quite went away. They were like cracks in a beautiful marble statue, small enough to ignore but hinting that something wasn't quite right beneath the surface. And then came a young man who would shatter the statue entirely and build something even more beautiful in its place. Albert Einstein was 26 years old in 1905, working as a patent clerk in Bern, Switzerland. He had failed to get an academic position after graduating. His job was to evaluate patent applications for electromagnetic devices. But in his spare time, during lunch breaks and evenings, he thought about physics. And in that single miraculous year, he published 4 papers that would transform our understanding of reality. One of those papers introduced what we now call special relativity, and it contained a bombshell that would eventually force a complete rethinking of gravity. Einstein showed that nothing can travel faster than light. This isn't just a technological limitation, something we might overcome with better engines. It's a fundamental law of the universe, woven into the fabric of reality itself. Light travels at about 186,000 miles per second, and this speed is the absolute cosmic speed limit. No particle, no signal, no information of any kind can exceed it. This might seem like an abstract point, but it created a devastating problem for Newton's gravity. Remember, in Newton's picture, gravity acts instantaneously across any distance. The sun pulls on Earth, and Earth responds immediately, even though they're 93 million miles apart. If the sun suddenly moved, Earth would feel the change in gravitational pull right away, with no delay whatsoever. But Einstein had just shown that nothing travels faster than light. Information cannot propagate instantly. If the sun moved, how could Earth know about it before light had time to carry the news? Light takes about 8 minutes to travel from the sun to Earth. Yet Newton's equations demanded that gravity work instantaneously. The two theories couldn't both be right. Something fundamental had to change. Einstein recognized this conflict immediately, and it haunted him. He spent the next 10 years, from 1905 to 1915, struggling to reconcile gravity with his new understanding of space and time. It was the most intellectually grueling decade of his life. He made wrong turns. He published papers with errors he later had to retract. He pushed himself to the limits of human thought. The breakthrough began with a simple observation that Einstein later called the happiest thought of my life. In 1907, Einstein was sitting in his chair at the patent office when a thought struck him. He imagined a person falling freely, perhaps from a roof. During the fall, that person would feel weightless. They wouldn't feel gravity pulling them down. From their perspective, there would be no gravitational force at all. This might seem obvious. Of course, you feel weightless when you're falling. But Einstein saw something deeper. The falling person isn't just failing to notice gravity. From their point of view, gravity has genuinely disappeared. All the effects of gravity, the pull toward the ground, the sensation of weight, vanish completely during free fall. Now consider the reverse situation. Imagine you're in a rocket ship in deep space, far from any planet or star. There's no gravity out there. You float freely, weightless, but now the rocket engines fire, accelerating the ship. Suddenly you feel pressed against the floor. If you drop a ball, it falls toward the floor. If you stand on a scale, it registers your normal weight. From inside that accelerating rocket, you cannot tell whether you're being accelerated through space or sitting on the surface of a planet. The experiences are identical. There is no experiment you could perform, no measurement you could make that would distinguish between acceleration and gravity. Einstein elevated this observation into a principle, the equivalence principle. Gravity and acceleration are fundamentally equivalent. They are not merely similar. They are, in some deep sense, the same thing. This principle became the foundation on which Einstein built his new theory of gravity, and it led him to a prediction that seemed almost absurd. Think about light in an accelerating spaceship. Imagine a laser beam entering through a window on one side of the ship, traveling across to the opposite wall. In the time it takes the light to cross the ship has accelerated upwards slightly. From inside the ship, the light appears to bend downward, curving toward the floor as it crosses. Now apply the equivalence principle. If you can't distinguish between acceleration and gravity, and if light bends in an accelerating ship, then light must also bend in a gravitational field. This was revolutionary. Newton's gravity said nothing about light being affected by gravity. Light had no mass, so it shouldn't feel gravitational pull. But Einstein was predicting that near a massive object like the sun, light rays should curve. Einstein first calculated how much light should bend in 1911. He got a value, but it was wrong because he hadn't yet completed his full theory. He predicted that starlight grazing the edge of the sun would bend by about 0.87 arc seconds. This was small but potentially measurable during a solar eclipse, when the sun's glare is blocked and stars near the sun become visible. German astronomers actually planned an expedition to observe the eclipse of 1914 from Crimea. They wanted to test Einstein's prediction, but World War I broke out, and the German scientists were captured by Russian forces. The experiment never happened. This turned out to be fortunate for Einstein. His 1911 calculation was based on incomplete physics. Had the measurement been made, it would have disagreed with his prediction, and his theory might have been dismissed. Instead, the war gave Einstein 4 more years to complete his work. And when he finished in 1915, he realized his earlier prediction was only half the correct value. The full theory, general relativity, emerged from Einstein's struggle with a profound question. If gravity bends light, why? What is the mechanism? Light follows straight paths through space. That's one of its defining properties. So if light appears to bend near a massive object, something must be happening to space itself. This is where Einstein made his greatest conceptual leap. He proposed that massive objects don't just pull on other objects, they warp the very fabric of space and time around them. Imagine space-time as a vast, stretched fabric, like a trampoline. When you place a heavy ball on a trampoline, it creates a depression. The fabric curves downward around the ball. Now roll a marble across the trampoline near the ball. The marble doesn't travel in a straight line, it curves toward the ball, following the contour of the depressed fabric. The marble isn't being pulled by a force from the ball, it's just following the shape of the surface it's rolling on. What looks like attraction is actually geometry. Einstein proposed that this is how gravity really works. The sun doesn't reach out across space and pull on the Earth. Instead, the sun's mass warps space-time around it, creating a curved region. Earth moves through this curved space-time, and what we interpret as the sun's gravitational pull is actually Earth following the contours of warped geometry. This is not just a different description of the same thing. It's a fundamentally different picture of what gravity is. For Einstein, gravity is geometry. It's the shape of space-time itself. The mathematics Einstein needed to describe curved space-time didn't exist in convenient form. He had to master a branch of mathematics called differential geometry, developed in the 19th century by mathematicians like Bernhard Riemann. It describes how to do geometry on curved surfaces, how to measure distances and angles when the surface itself is bent or warped. Einstein struggled with this mathematics for years. In 1912, he wrote to a friend that he had never worked so hard in his life. The mathematics of curved space-time was immensely difficult, even for a genius of Einstein's caliber. He enlisted the help of his mathematician friend Marcel Grossmann. Together, they developed the tools Einstein needed. The final equations, known as Einstein's field equations, are beautiful but complex. They relate the curvature of space-time to the distribution of mass and energy within it. Mass tells space-time how to curve, and curved space-time tells mass how to move. This elegant reciprocity captures the essence of general relativity. Einstein presented his completed theory to the Prussian Academy of Sciences in November 1915. He was exhausted but triumphant, and almost immediately, he put his theory to the test. Remember Mercury's orbit, with its unexplained 43 arcseconds of extra precession per century. Newton's theory couldn't account for it. Astronomers had searched in vain for a planet called Vulcan that might explain the discrepancy. None existed. Einstein plugged Mercury's orbital parameters into his new equations. The calculation was complex, but when he worked through it, the answer emerged: 43 arcseconds per century. Exactly what the observations showed. No fudge factors, no adjustments. His theory predicted precisely the amount of extra precession that had puzzled astronomers for decades. Einstein later said that when he saw this result, he felt physical palpitations of the heart. The precession of Mercury was the first triumph of general relativity, and it came from the theory itself, without any input from the observations it was trying to explain. This is the hallmark of a great theory. It doesn't just fit the data. It explains things you weren't even trying to explain. But the precession of Mercury was a refinement of an existing observation. Einstein's theory also made new predictions that could be tested directly. The most dramatic prediction was the bending of starlight. Einstein's full theory predicted that light passing near the sun would bend by 1.75 arcseconds, exactly twice his earlier incorrect estimate. This was enough to be measured, but only during a total solar eclipse, when the sun's blinding light is blocked and stars near the sun become visible. Arthur Eddington, a British astronomer, was one of the few scientists in England who took Einstein's work seriously during the war years. In 1919, with the war ended, Eddington organized 2 expeditions to observe a solar eclipse that would pass over South America and West Africa. One team went to Sobral, Brazil. Eddington himself led a team to the island of Principe off the coast of Guinea. The expeditions faced serious challenges. Principe was clouded over for much of the eclipse. The equipment malfunctioned. Only a few usable photographs were obtained. But when Eddington analyzed the plates, measuring the positions of stars near the sun and comparing them to photographs of the same stars when the sun was elsewhere in the sky, the stars appeared shifted. They appeared moved outward, away from the sun, by about the amount Einstein had predicted. The announcement came in November 1919 at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The verdict: Einstein's theory was confirmed. Newton had been overthrown. The news exploded across the world. Revolution in science, declared the Times of London. New theory of the universe. Newtonian ideas overthrown. Einstein became an overnight celebrity, perhaps the first scientist to achieve true global fame. His wild hair and eccentric manner became iconic. His name became synonymous with genius. But what did this confirmation actually mean? What was Einstein saying about the nature of reality? The core insight is this: space and time are not separate, unchanging entities that provide a stage for physical events. Instead, space and time are woven together into a single 4-dimensional fabric called spacetime. And this fabric is dynamic. It responds to mass and energy. It bends, warps, and curves. When you stand on Earth's surface, space-time is curved around you. The curvature is subtle, imperceptible to your senses, but it's real and measurable. That curvature is what we experience as gravity. You don't feel a force pulling you down. You feel the ground pushing up on you, preventing you from following your natural path through curved space-time. Here's a way to think about it. If you were in deep space, far from any mass, and you threw a ball, it would travel in a straight line forever. There would be no force to deflect it. In Einstein's language, the ball would follow a geodesic, the straightest possible path through space-time. Now put a massive object nearby. The ball still follows a geodesic, still takes the straightest possible path. But space-time itself is curved, so the straightest path is no longer what we would call a straight line in 3-dimensional space. It's a curve. The ball bends toward the massive object, not because it's being pulled by a force, but because curved space-time has redefined what straight means. This applies to everything, including light. Light always follows geodesics, but near massive objects, geodesics are curved, so light curves, not because a force is acting on it, but because space itself is bent. The predictions of general relativity extend far beyond bending light and explaining Mercury's orbit. Einstein's theory predicts that gravity affects time. Where gravity is stronger, time passes more slowly. This sounds like science fiction, but it's been measured directly. In 1959, physicists Robert Pound and Glenn Rebka performed an experiment at Harvard. They measured the frequency of gamma rays at the bottom and top of a tower. The rays emitted at the bottom, where gravity is slightly stronger, had a lower frequency when they reached the top. Time was running slower at the bottom of the tower. The effect is tiny on Earth, but it's measurable with sensitive equipment, and it has practical consequences. GPS satellites orbit at about 12,500 miles altitude, where gravity is weaker than at Earth's surface. Their onboard clocks run faster by about 38 microseconds per day when you account for both gravitational time dilation and the opposing effect of their orbital velocity. This sounds insignificant, but if GPS didn't correct for these relativistic effects, position calculations would drift by miles within a day. Your phone's navigation works because engineers account for Einstein's curved spacetime. Einstein's theory also predicts gravitational redshift. Light climbing out of a gravitational field loses energy. It doesn't slow down. Light always travels at light speed, but its frequency decreases. Lower frequency means the light shifts toward the red end of the spectrum. This has been measured for light-escaping stars and even for light climbing short distances in Earth's gravity. Perhaps the most dramatic prediction of general relativity concerns what happens when space-time is curved extremely, not slightly as on Earth, but so severely that nothing can escape. Take a massive star that has exhausted its nuclear fuel. Without the outward pressure from fusion to support it, the star collapses under its own gravity. If the star is massive enough, there's nothing that can stop the collapse. The matter falls inward, space-time curves more and more severely, and eventually the curvature becomes so extreme that even light, following geodesics through that warped region, cannot escape. This is a black hole. The boundary around it, the point of no return, is called the event horizon. Cross the event horizon, and there's no path through space-time that leads back out. All geodesics inside the event horizon lead inward, toward the center. Einstein's equations predicted black holes, but Einstein himself didn't believe they could actually exist in nature. He thought the extreme conditions required were too bizarre to be physical. For decades, black holes were a theoretical curiosity, a mathematical consequence of the equations, but not necessarily real. We now know they're very real. We've observed stars orbiting invisible massive objects at the centers of galaxies. We've detected X-rays from gas heating up as it spirals into black holes. We've measured gravitational waves from black holes colliding. And in 2019, the Event Horizon Telescope produced the first direct image of a black hole, the supermassive one at the center of galaxy M87. The image showed a dark shadow, the black hole's silhouette, surrounded by glowing gas. It looked exactly as general relativity predicted. Another prediction of Einstein's theory took a century to confirm directly. When massive objects accelerate, they should create ripples in space-time that propagate outward at the speed of light. These gravitational waves are like ripples on a pond, but instead of water oscillating, it's space itself, stretching and compressing. Einstein predicted gravitational waves in 1916, but he doubted they could ever be detected. The waves are incredibly weak. Even violent cosmic events create ripples so tiny that they stretch and compress distances by less than the width of a proton. In 1974, Russell Hulse and Joseph Taylor discovered a binary pulsar, two neutron stars orbiting each other. General relativity predicted that such a system should emit gravitational waves, slowly losing energy and spiraling together. Hulse and Taylor observed the system for years and found that the orbital period was decreasing at exactly the rate Einstein's equations predicted. This was indirect evidence for gravitational waves, and it earned them the Nobel Prize in 1993. Direct detection came in 2015, exactly 100 years after Einstein published General Relativity. The LIGO observatories in Louisiana and Washington state both registered a signal from two black holes merging over 1 billion light-years away. The gravitational waves stretched and compressed LIGO's 4-kilometer arms by about 1,000th the width of a proton. The detection confirmed that gravitational waves exist, travel at the speed of light, and behave exactly as Einstein predicted. General relativity has also been tested in extreme environments near the supermassive black hole at the center of our own galaxy. Stars orbit this invisible mass at speeds up to several percent of light speed. Their motions have been tracked for decades. Every prediction of general relativity has been confirmed, including the way time slows for stars passing close to the black hole. So where does this leave us? Einstein's general relativity has passed every test we've thrown at it. It explains Mercury's orbit, predicts the bending of light, describes black holes, accounts for gravitational waves, and correctly describes time dilation in gravitational fields. It's one of the most successful theories in the history of science. But there's something deeply unsatisfying about this success. Einstein replaced Newton's mysterious force with curved spacetime. This was an enormous conceptual advance. But what is spacetime? Why does mass curve it? These questions remain unanswered. General relativity describes how mass and spacetime interact, but it doesn't explain why they interact this way. It's still, at bottom, a description rather than an explanation. Einstein gave us the geometry of gravity, the mathematical rules that govern how spacetime curves, but he didn't tell us what spacetime is made of. He didn't explain the mechanism by which mass creates curvature. The equations work beautifully, but the underlying reality remains mysterious. And there's a deeper problem, one that would trouble Einstein for the rest of his life and continues to trouble physicists today. General relativity doesn't play well with quantum mechanics. Quantum mechanics is the theory that describes the behavior of matter at the smallest scales. It governs atoms, electrons, photons, all the particles that make up the world, and it's been tested with even greater precision than general relativity. The predictions of quantum mechanics have been confirmed to more than 10 decimal places. Every electronic device you've ever used works because quantum mechanics correctly describes how electrons behave in semiconductors. But when you try to combine quantum mechanics with general relativity, disaster strikes. The mathematics produces nonsensical results, infinite answers where there should be finite ones. The two great pillars of modern physics, each spectacularly successful in its own domain, refuse to work together. This incompatibility suggests that general relativity, despite its successes, is not the final word on gravity. Something deeper must lie beneath it. A quantum theory of gravity that would explain how space-time behaves at the smallest scales, where quantum effects become important. We don't have that theory yet. Physicists have been searching for it for decades. String theory, loop quantum gravity, and other approaches have been proposed, but none has been confirmed. The quantum nature of gravity remains one of the biggest unsolved problems in physics. What is gravity? Newton said it was a force. Einstein said it was curved space-time. Both descriptions work brilliantly in their domains, but neither tells us what gravity ultimately is. Neither explains why masses curve space-time or why curved space-time guides the motion of masses. Neither reconciles gravity with quantum mechanics. We've made enormous progress since Newton watched that apple fall. We understand gravity far better than our ancestors did. We can predict its effects with stunning accuracy. We've used it to discover new planets, detect black holes, and observe gravitational waves from across the cosmos. But the deepest questions remain open. What is gravity? Why does it exist? How does it work at the quantum level? These mysteries await the next revolution, the next Einstein who will see what we cannot yet see and reshape our understanding once again. We've explored what gravity is, or at least what our best theories tell us it might be. Newton gave us equations. Einstein gave us curved space-time. But now, let's step back and witness what gravity actually does when given 13.8 billion years to work with. Because gravity isn't just a theoretical concept that physicists argue about. It's the sculptor of everything. Every structure you can see in the night sky, every star, every galaxy, every vast web of matter stretching across billions of light years exists because gravity pulled it together. Without gravity, the universe would be nothing but a thin, cold fog of particles drifting apart forever. No stars, no planets, no light, no warmth, no us. Gravity took the raw material of the early universe and built a cosmos. Let's go back to the beginning. Not quite the beginning, because we don't fully understand the first instant of the Big Bang. But shortly after, when the universe was a fraction of a second old, something extraordinary was happening. Space was expanding explosively. Energy was everywhere, so intense that particles and antiparticles were constantly forming and annihilating. As the universe cooled, Quarks combined to form protons and neutrons. A few minutes after the Big Bang, these protons and neutrons fused together to form the nuclei of hydrogen, helium, and tiny amounts of lithium. This process, called Big Bang nucleosynthesis, happened in the first 20 minutes of cosmic history. After that, the universe was too cool and diffuse for further fusion. For the next 380,000 years, the universe was a hot, opaque plasma. Photons couldn't travel far without scattering off free electrons. Then, as the temperature dropped below about 3,000 degrees, electrons combined with nuclei to form neutral atoms. Suddenly, the universe became transparent. Light could travel freely. This moment left an imprint we can still see today, the cosmic microwave background radiation, a faint glow of ancient light that fills all of space. At this point, the universe was almost perfectly uniform. If you could have floated in that ancient cosmos and looked around, you would have seen the same thing in every direction. A faint red glow of cooling gas, mostly hydrogen, spread evenly through space. Almost evenly. There were tiny variations. Quantum fluctuations from the first instant of the Big Bang had been stretched by cosmic expansion into density variations across space. Some regions were slightly denser than average, by about 1 part in 100,000. Other regions were slightly less dense. These variations were minuscule, but they were enough. In the denser regions, gravity had a little more to work with. More matter meant stronger gravitational pull. Stronger pull meant more matter falling in. More matter meant even stronger pull. This feedback loop, slow at first, began to amplify the tiny initial differences. Over hundreds of millions of years, the denser regions grew denser. They attracted matter from surrounding regions, which became emptier. The universe began to develop structure, like frost-forming patterns on a window. The first generation of stars appeared perhaps 100 to 200 million years after the Big Bang. We call these population 3 stars, and none of them exist today. They were giants, perhaps hundreds of times the mass of our Sun, made of pure hydrogen and helium because no heavier elements existed yet. They burned hot and fast, living only a few million years before exploding as supernovae. Those explosions were crucial. Inside these first stars, nuclear fusion had built heavier elements: carbon, oxygen, nitrogen, silicon, iron. When the stars exploded, they scattered these elements into space. The next generation of stars formed from gas enriched with these heavier elements, and when those stars died, they enriched the gas further. Every heavy element in your body was forged inside a star. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of it was created by nuclear fusion in stellar cores and scattered across space by supernova explosions. You are, quite literally, made of star stuff. But let's focus on what gravity does, not just to individual stars, but to the universe as a whole. As the universe aged, gravity continued to pull matter together on ever larger scales. Small clumps merged to form larger clumps. Gas clouds containing billions of solar masses collapsed to form protogalaxies. Within these protogalaxies, smaller regions collapsed to form individual stars. The process wasn't gentle. Collisions were common. Smaller structures merged into larger ones. Early galaxies were chaotic, irregular blobs of stars and gas, constantly disturbed by mergers and interactions. Over billions of years, gravity sorted things out. Many galaxies settled into more regular shapes, spirals with rotating disks and graceful arms, or ellipticals with smooth, rounded profiles. Our own Milky Way formed this way. It began as a smaller protogalaxy, perhaps 12 or 13 billion years ago. Over cosmic time, it consumed dozens of smaller galaxies, absorbing their stars and gas. We can still see the evidence of these ancient mergers. Streams of stars in unusual orbits around the galactic center are the remnants of galaxies the Milky Way devoured long ago. The Sagittarius dwarf elliptical galaxy is being consumed right now. It orbits the Milky Way, passing through the galactic disk periodically. Each passage strips away more of its stars. In a few 100 million years, it will be completely absorbed, its stars scattered and mixed with the Milky Way's own. This is what gravity does over cosmic time. It builds things up by pulling smaller things together. It's patient, working over millions and billions of years, but relentless. Eventually, gravity gathers everything it can reach. Let me take you deeper into this process by following the life of a single cloud of gas. Imagine a molecular cloud, a vast region of cold gas and dust floating in interstellar space. This cloud might be 100 light years across and contain enough matter to make thousands of stars. The gas is cold, only about 10 degrees above absolute zero, and dark. No light comes from within it. It's just a cold, dark mass of mostly hydrogen, with traces of heavier elements and tiny grains of dust. Now imagine something disturbs this cloud. Perhaps a shockwave from a nearby supernova passes through, compressing the gas. Perhaps the cloud passes through a spiral arm of the galaxy, where gravity is slightly stronger. Perhaps it simply reaches a critical density on its own. Whatever the trigger, parts of the cloud begin to collapse. Gravity pulls gas toward the densest regions. As the gas falls inward, it speeds up, converting gravitational potential energy into kinetic energy. The atoms move faster, which means the gas heats up. The collapsing region gets denser and hotter. But something else happens too. The cloud was rotating slightly, as most things in the universe do. As it collapses, it spins faster, like an ice skater pulling in their arms. This spin prevents the gas from falling straight to the center. Instead, it settles into a flattened disk with a dense, hot core. In the core, temperatures and pressures climb toward extraordinary values. When the temperature reaches about 10 million degrees, hydrogen nuclei start moving fast enough to overcome their electrical repulsion. They collide and fuse, forming helium and releasing energy. A star is born. The energy from fusion creates pressure that pushes outward, counteracting gravity's inward pull. The star reaches a stable equilibrium. It will remain in this state for millions or billions of years, depending on its mass, steadily fusing hydrogen into helium and radiating energy into space. Meanwhile, in the disk around the young star, other things are happening. Dust grains collide and stick together, forming larger grains, then pebbles, then rocks, then planetesimals. Gravity pulls these objects together, building planets. The larger ones attract gas from the disk, becoming gas giants. The smaller ones remain rocky. After a few million years, the remaining gas is blown away by the young star's radiation, and a planetary system is revealed. Gravity has transformed a cold, dark cloud into a shining star surrounded by orbiting worlds. This is happening right now, all over the universe. The Orion Nebula, visible as a fuzzy patch in the Sword of Orion, is a stellar nursery about 1,300 light-years from Earth. Deep within its glowing gas clouds, new stars are forming. Some of them probably have planets. In a few million years, those planets might cool and stabilize. In a few billion years, life might emerge on some of them. Gravity makes all of this possible. But gravity doesn't just create, it also destroys, or rather, it transforms. And some of gravity's most dramatic transformations happen when stars die. A star like our Sun will die relatively peacefully. In about 5 billion years, it will exhaust the hydrogen in its core. The core will contract under gravity, heating up until hydrogen fusion begins in a shell around the core. This extra energy will cause the outer layers to expand enormously. The Sun will become a red giant, swelling so large that it might engulf Mercury and Venus. Eventually, the core will get hot enough to fuse helium into carbon and oxygen, but the sun isn't massive enough to fuse elements beyond that. When the helium runs out, the core will contract into a white dwarf, a dense ball of carbon and oxygen about the size of Earth, supported against further collapse by electron degeneracy pressure, a quantum mechanical effect. The outer layers will drift away as a planetary nebula, a beautiful shell of glowing gas that will eventually disperse into space. A white dwarf is gravity's compromise. It has compressed the core of a star to incredible density, about 1,000,000 times denser than water, but quantum mechanics prevents further collapse. The white dwarf will cool slowly over billions of years, eventually becoming a cold, dark cinder. But massive stars tell a different story. Consider a star 20 times the mass of our sun. It burns through its hydrogen fuel much faster than the sun will, in perhaps 10 million years rather than 10 billion. When the hydrogen is gone, it fuses helium. When the helium is gone, it fuses carbon, then neon, then oxygen, then silicon. Each stage is shorter than the last. Silicon fusion, the final stage, lasts only about a day. At the end of silicon fusion, the core is made of iron, and here the star reaches a crisis. Iron fusion doesn't release energy, it absorbs energy. The core can no longer generate the pressure needed to support the overlying layers. In less than a second, catastrophe strikes. The iron core collapses under gravity. Electrons are squeezed into protons, forming neutrons and releasing a flood of neutrinos. The core, which was about the size of Earth moments ago, compresses to about 12 miles across. The collapse releases an enormous amount of gravitational potential energy. This energy, carried mostly by neutrinos, blows the outer layers of the star apart in a supernova explosion. For a few weeks, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. What's left behind is determined by how much mass remains in the collapsed core. If the core is between about 1.5 and 3 solar masses, it becomes a neutron star. This is an object so dense that the mass of the sun is compressed into a sphere roughly the size of a city. The density is about 1 billion tons per cubic centimeter. If you could somehow bring a teaspoon of neutron star material to Earth, it would weigh about as much as Mount Everest. Neutron stars have surfaces, but you would never want to land on one. The gravity is about 200 billion times Earth's surface gravity. If you were to fall from a height of 1 meter onto a neutron star, you would hit the surface at about 2,000 kilometers per second, releasing energy equivalent to several nuclear bombs. You wouldn't survive long enough to notice. Neutron stars also have intense magnetic fields, typically 1 trillion times stronger than Earth's. Some neutron stars, called magnetars, have fields thousands of times stronger still. The physics at the surface of a magnetar is almost incomprehensibly extreme, but neutron stars are not gravity's final word. If the collapsing core is too massive, exceeding about 3 solar masses, not even neutron degeneracy pressure can halt the collapse. Nothing can. Gravity wins completely. The core continues collapsing, falling through the threshold we call the event horizon, beyond which no information can escape. What happens after that, we don't truly know. General relativity predicts that the collapse continues to a singularity, a point of infinite density, where our equations break down. But most physicists believe this prediction indicates a failure of our theory rather than a description of reality. Something must happen at these extreme conditions, some quantum effect we don't yet understand, that prevents a true singularity from forming. What we do know is what happens outside the event horizon. Space is warped so severely that all paths through spacetime lead inward. Light trying to escape is bent back. Time, as measured by a distant observer, seems to stop at the event horizon. The black hole appears frozen, a dark sphere from which nothing emerges. We used to think black holes were rare and exotic. Now we know they're everywhere. Every large galaxy appears to have a supermassive black hole at its center. These monsters contain millions to billions of solar masses. Our galaxy's central black hole is on the smaller end of this range. The one at the center of galaxy M87, the first ever directly imaged, is a true monster nearly 2,000 times more massive. How did these supermassive black holes form? We're not sure. They might have grown from smaller black holes that merged over billions of years. They might have formed directly from the collapse of enormous gas clouds in the early universe, creating what astronomers call direct collapse black holes. Or they might have grown from the remnants of the very first generation of massive stars. Whatever their origin, supermassive black holes play a crucial role in galaxy evolution. When gas falls toward a supermassive black hole, it forms an accretion disk, a swirling vortex of hot matter. Friction in the disk heats the gas to millions of degrees, making it glow brilliantly in X-rays and other wavelengths. Some of this energy is channeled into jets, beams of particles accelerated to nearly the speed of light that shoot outward from the poles of the black hole. These jets can extend for millions of light years, far beyond the galaxies that host them. They carry enormous amounts of energy into intergalactic space. When they interact with the gas surrounding galaxies, they can heat it up, preventing it from cooling and forming new stars. In this way, black holes regulate the growth of their host galaxies. Too much gas falling in triggers powerful jets that blow away surrounding material. Too little gas and the black hole goes quiet. This feedback mechanism helps explain why supermassive black holes and their host galaxies seem to grow together, maintaining a consistent relationship between black hole mass and galaxy properties across the universe. Now let's zoom out even further. Galaxies aren't scattered randomly through space. They're organized into a vast cosmic web, a network of filaments and walls surrounding enormous empty voids. This structure spans the entire observable universe, extending for tens of billions of light years. How did this structure form? The same way everything else formed. Gravity amplified tiny initial variations. In the early universe, regions that were slightly denser attracted more matter and became denser still. Regions that were slightly less dense lost matter to their surroundings and became emptier. Over billions of years, this process created the cosmic web we see today. The filaments of the cosmic web are rivers of dark matter and diffuse gas, with galaxies strung along them like beads on a string. Where filaments intersect, you find galaxy clusters, dense collections of hundreds or thousands of galaxies held together by gravity. The largest clusters contain several trillion solar masses, including enormous quantities of dark matter and hot intergalactic gas. The voids are nearly empty. They can be hundreds of millions of light years across, containing almost no galaxies. If you were somehow transported to the center of a void and looked around, the nearest significant galaxy might be 50 or 100 million light years away. The sky would be almost empty, a stark contrast to our location in a relatively crowded galactic neighborhood. This web-like structure is a direct result of gravity working on the initial conditions set by the Big Bang. Computer simulations that start with the observed properties of the early universe and let gravity operate over billions of years produce cosmic webs that look remarkably like what we observe. This is powerful evidence that we understand the basic physics correctly. The Milky Way is part of the Local Group, a collection of more than 80 galaxies bound together by gravity. The largest members are the Milky Way and Andromeda. The rest are smaller dwarf galaxies. The Local Group is part of the Virgo supercluster, which contains about 100 galaxy groups and clusters spread across 110 million light years. And the Virgo supercluster is part of an even larger structure called Laniakea, containing about 100,000 galaxies spread across 520 million light years. Gravity also drives the dynamic evolution of cosmic structures. Galaxies don't just sit still, they move, pulled by the gravity of other galaxies and the overall distribution of matter. The Milky Way and Andromeda are falling toward each other at about 70 miles per second. In about 4.5 billion years, they will collide and merge into a larger galaxy. This might sound catastrophic, but actual collisions between stars will be rare. Stars are so far apart that the two galaxies will largely pass through each other. However, gravitational interactions will fling stars into new orbits, disrupting the spiral structures of both galaxies. Eventually, after several passes, the two galaxies will settle into a single large elliptical galaxy. Let's talk about gravitational waves, because they represent one of the most spectacular confirmations of Einstein's theory and one of the most powerful tools for studying extreme gravity. When massive objects accelerate, they create ripples in space-time that propagate outward at the speed of light. These are gravitational waves. Every accelerating mass creates them, but for most objects, the waves are so weak they're undetectable. Only the most extreme events produce waves strong enough for us to observe. As we discussed earlier, LIGO's first detection in 2015 confirmed that gravitational waves are real and behave exactly as Einstein predicted. But that detection was just the beginning. What matters for understanding cosmic structure is what gravitational wave astronomy has revealed since then. Every detection tells us something new. The masses of the merging black holes, how fast they were spinning, how they were oriented. We've discovered black holes larger than stellar evolution models predicted. We've found them in unexpected configurations. Each event is a window into extreme gravity that we couldn't access any other way. Since that first detection, LIGO and its European counterpart Virgo have detected nearly 100 gravitational wave events. Most are merging black holes, but some are neutron star mergers. In August 2017, LIGO detected a neutron star merger that was also observed across the electromagnetic spectrum, from gamma rays to radio waves. This multi-messenger observation confirmed that gravitational waves travel at the speed of light, as Einstein predicted, and showed that neutron star mergers produce heavy elements like gold and platinum. Gravitational wave astronomy is a new field, less than a decade old. But it's already revealing aspects of gravity and the universe that we couldn't study any other way. Future detectors, both on ground and in space, will observe gravitational waves from even more extreme events, including the mergers of supermassive black holes and possibly echoes from the very early universe. One final cosmic phenomenon shaped by gravity: the expansion of the universe itself. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This wasn't because we're at the center of some cosmic explosion. It's because space itself is expanding. Every point in the universe sees distant galaxies receding. It's like dots on a balloon that's being inflated. Every dot moves away from every other dot. For most of the 20th century, astronomers assumed this expansion was slowing down. After all, gravity attracts. The mutual gravitational pull of all the matter in the universe should be decelerating the expansion. But in 1998, two teams of astronomers discovered something shocking. They were measuring distant supernovae to determine how the expansion rate had changed over time. What they found was the opposite of what anyone expected. The expansion wasn't slowing down, it was speeding up. Something is pushing the universe apart, counteracting gravity on the largest scales. We call this something dark energy, and we have almost no idea what it is. It makes up about 68% of the total energy content of the universe, yet we can't explain it. It might be a property of space itself, a kind of repulsive pressure built into the fabric of space-time, or it might be something else entirely. One possibility is that dark energy is the cosmological constant, a term Einstein added to his equations in 1917 and later called his greatest blunder. The cosmological constant represents a constant energy density of empty space. If space itself has a small but positive energy density, it would produce exactly the kind of accelerating expansion we observe. But there's a problem. When physicists try to calculate what this energy density should be using quantum mechanics, they get a wildly wrong answer. We'll explore this disturbing mismatch in detail later, because it represents one of the deepest failures in all of physics, a failure that sits right at the intersection of gravity and quantum mechanics. But there's another mystery lurking in this picture. When astronomers measure the motions of galaxies within clusters, they find something strange. The galaxies are moving too fast. If you add up all the visible matter in a cluster, the stars and hot gas and everything else we can detect, there isn't enough mass to hold the cluster together. The galaxies should be flying apart. The same problem appears on the scale of individual galaxies. When we measure how fast stars orbit in the outer regions of spiral galaxies, we find they're moving faster than they should if the only gravity comes from visible matter. According to Newton's and Einstein's equations, stars in the outer parts of galaxies should move more slowly. But they don't. They move at roughly constant speeds, regardless of their distance from the galactic center. This is the dark matter problem. Something is providing extra gravity, holding galaxies and clusters together, but we can't see it. It doesn't emit light. It doesn't absorb light. It seems to interact with normal matter only through gravity. Dark matter makes up about 27% of the total energy content of the universe, about 5 times as much as normal matter. It's not made of protons, neutrons, and electrons like the matter we're familiar with. It's something else entirely, some particle or substance we haven't yet identified. What is dark matter? We don't know. And what is dark energy? We don't know that either. Together, these mysterious components make up 95% of the universe's energy content. The ordinary matter we're made of, the stuff we understand, is only 5%. We live in a universe dominated by things we cannot see and do not understand. Gravity built everything we know, but the cosmic stage is far stranger than we imagined. And solving the mysteries of dark matter and dark energy may require solving the mystery of gravity itself. So, gravity shapes the universe at every scale. It forms stars and planets. It creates black holes and neutron stars. It assembles galaxies and clusters and the cosmic web. It curves space-time and creates gravitational waves. And yet, working against it on the largest scales, there seems to be something we don't understand at all, something that's accelerating the expansion of the cosmos. This is the cosmic masterpiece of gravity. Beautiful, complex, and still not fully understood. After everything we've explored, after Newton's elegant mathematics and Einstein's revolutionary curved space-time, after witnessing gravity sculpt stars and galaxies and the cosmic web itself, you might think we've figured gravity out. We can calculate its effects with extraordinary precision. We've detected gravitational waves from colliding black holes over 1 billion light-years away. We've imaged the shadow of a black hole and watched stars whip around the supermassive monster at the center of our galaxy. Surely, gravity is a solved problem. It isn't. Not even close. Gravity is actually the most problematic of all the fundamental forces. It's the one that keeps theoretical physicists awake at night, the one that refuses to fit into our deepest frameworks, the one that hints at something profoundly wrong with our understanding of reality itself. And the reasons for this are both fascinating and deeply unsettling. Let me show you why. There are 4 fundamental forces in the universe. Gravity is the one you know best. Electromagnetism is the one that holds atoms together, makes light, and powers every electronic device you've ever used. The strong nuclear force binds protons and neutrons together in atomic nuclei. The weak nuclear force governs certain types of radioactive decay. 3 of these forces have been successfully described by quantum mechanics. We have quantum theories of electromagnetism, the strong force, and the weak force. These theories are called quantum field theories, and they work spectacularly well. In quantum field theories, forces aren't mysterious influences that reach across space. Instead, forces are carried by particles. Electromagnetism is carried by photons. When two electrons repel each other, they're actually exchanging photons. The strong force is carried by particles called gluons. The weak force is carried by W and Z bosons. These force-carrying particles are called bosons, and their exchange is how all known forces work at the quantum level. When you push against a wall, what you're really feeling is the electromagnetic repulsion between the electrons in your hand and the electrons in the wall, mediated by virtual photons bouncing back and forth faster than you could ever perceive. Quantum electrodynamics, the quantum theory of electromagnetism, is the most precisely tested theory in the history of science. Its predictions have been confirmed to more than 10 decimal places. That's like predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. No other theory in any field of science has achieved such precision. So naturally, physicists have tried to create a quantum theory of gravity. The force-carrying particle for gravity would be called the graviton. Just as photons carry electromagnetic force, gravitons would carry gravitational force. In principle, the mathematics should work the same way, but it doesn't. When physicists try to calculate gravitational interactions at the quantum level, using the same techniques that work so beautifully for other forces, something goes horribly wrong. The equations explode. Instead of getting finite, sensible answers, you get infinities. Not just one infinity, but cascading infinities that multiply and compound, rendering the calculations meaningless. This isn't a minor technical problem. It's a fundamental breakdown. With other quantum field theories, infinities also appear in the calculations, but physicists developed a technique called renormalization to handle them. The infinities can be absorbed into redefinitions of the theory's fundamental constants, leaving behind finite predictions that match experiments. It's a bit like having a measuring stick that's slightly warped. Using the warped stick gives you wrong answers, but if you carefully account for the warping, you can still make accurate measurements. Renormalization works for electromagnetism. It works for the strong force. It works for the weak force. But it doesn't work for gravity. Gravity is what physicists call non-renormalizable. The infinities can't be absorbed. They keep appearing at every level of calculation in ever more uncontrollable ways. There's no consistent way to extract finite predictions from a straightforward quantum theory of gravity. This means something profound. Our best theory of gravity, Einstein's general relativity, is fundamentally incompatible with our best theory of matter, quantum mechanics. These two great pillars of 20th century physics, each spectacularly successful in its own domain, cannot be combined into a single coherent framework. Both theories work. General relativity describes gravity with extraordinary accuracy. Quantum mechanics describes the behavior of particles with extraordinary accuracy. But they can't both be completely right, because they contradict each other at a fundamental level. Where does this contradiction matter? Mostly, it doesn't. For everyday phenomena, even for most astronomical phenomena, gravity is so weak compared to other forces that quantum effects are negligible. You can ignore quantum mechanics when calculating planetary orbits or the trajectories of spacecraft. You can ignore gravity when calculating the behavior of atoms and molecules. But there are places where both gravity and quantum mechanics matter simultaneously. And there, our physics breaks down completely. Inside a black hole, for example. At the singularity, where all the mass has collapsed to a point, density becomes infinite. Space-time curvature becomes infinite. General relativity's equations break down, producing nonsensical results. Quantum effects should be important at such extreme conditions, but we have no way to calculate them. We literally cannot describe what happens at the center of a black hole because we don't have a theory that works there. The same problem arises at the very beginning of the universe. According to general relativity, the Big Bang started from a singularity, a state of infinite density and temperature. But what does infinite density even mean? What happened at that first instant? What determined the initial conditions that led to the universe we observe? We don't know, because our theories fail precisely where we need them most. These aren't academic questions. The center of every black hole is inaccessible to our physics. The origin of everything we see around us is beyond our ability to describe. Our theories have a gaping hole right at the foundations of reality. This is why physicists have spent decades searching for a quantum theory of gravity, not just for intellectual satisfaction, though that matters too, but because there are real, important questions we cannot answer without one. Several approaches have been proposed. Let me tell you about the most prominent. String theory is probably the one you've heard of. It emerged in the 1970s and became the dominant approach to quantum gravity by the 1980s and 90s. The core idea is radical. What if the fundamental constituents of the universe aren't point-like particles but tiny vibrating strings of energy? These strings would be unimaginably small, about 10 to the minus 35 meters, a scale called the Planck length. At this size, a string would be as small compared to a proton as a proton is compared to the entire solar system. Different vibration patterns of these strings would correspond to different particles. One vibration pattern gives you an electron, another gives you a quark, another gives you a photon, and crucially, one vibration pattern gives you a graviton. String theory naturally incorporates gravity. It doesn't have to be added separately. The graviton just emerges as one of the possible string vibrations, and the mathematics of string theory seems to avoid the infinities that plague other approaches to quantum gravity. This sounds promising, and many physicists have devoted their careers to developing string theory in extraordinary mathematical detail. But there are problems. String theory requires extra dimensions of space. The mathematics only works if the universe has not 3 spatial dimensions but 9, or in some versions 10. Where are these extra dimensions? String theorists say they're curled up so small that we can't detect them, rolled into tiny shapes at every point in space. This isn't necessarily wrong. We have no direct evidence against extra dimensions, but we have no direct evidence for them either. The extra dimensions are a prediction of string theory, but we have no way to test this prediction with any technology we can currently imagine building. Even more troubling, string theory doesn't make a single unique prediction about our universe. Instead, it exists in a vast landscape of possible solutions, perhaps 10 to the 500 different versions, each corresponding to a different way the extra dimensions could be curled up. Each version would give a universe with different particles, different forces, different physical constants. 10 to the 500 is an unimaginably large number. It's far more than the number of atoms in the observable universe. If string theory is correct, how do we know which version describes our universe? We have no way to calculate this from first principles. The theory itself doesn't tell us. Some string theorists have embraced this landscape, suggesting that perhaps all these possible universes actually exist, and we simply find ourselves in one that allows for the existence of observers like us. This is called the anthropic principle, and many physicists find it deeply unsatisfying. It feels less like an explanation and more like a surrender. After more than 40 years of intense work by thousands of brilliant physicists, string theory has made no experimentally testable predictions that could distinguish it from other approaches. It remains a beautiful mathematical structure with no direct connection to observable reality. Loop quantum gravity is a different approach. Instead of adding extra dimensions, it focuses on quantizing spacetime itself. The core idea is that space is not continuous. At the smallest scales, space is granular, made up of discrete units. Think of it like this. From a distance, a piece of fabric looks smooth and continuous. But look closely enough, and you see it's woven from individual threads. Loop quantum gravity suggests that space-time is similar, appearing smooth at large scales, but revealing a discrete structure at the Planck scale. In this picture, space is built from tiny loops or nodes, connected by links, forming a kind of quantum foam. The familiar smooth space-time of general relativity emerges from averaging over this underlying quantum structure, just as the smooth appearance of fabric emerges from averaging over the individual threads. Loop quantum gravity makes some interesting predictions. It suggests that the Big Bang might not have been a true singularity. Instead, the universe might have bounced, collapsing from a previous state and then expanding again. This is called the Big Bounce. The singularity is avoided because space itself has a minimum possible size. You can't squeeze the universe smaller than the Planck length, so the density never actually becomes infinite. Similarly, loop quantum gravity suggests that black hole singularities might not be true singularities. The collapse might stop at some extremely high but finite density, with the matter transitioning to a new state we don't yet understand. These are fascinating possibilities, but loop quantum gravity has its own problems. It's less mathematically developed than string theory. It's difficult to show that general relativity emerges from it in the appropriate limit, and like string theory, it makes predictions that are extremely difficult to test with any foreseeable technology. There are other approaches too. Causal set theory proposes that space-time is fundamentally a discrete set of points with causal relationships between them, and the geometry of space-time emerges from these relationships. Asymptotic safety suggests that gravity might become well-behaved at high energies, with the infinities taming themselves in a way that hasn't been fully worked out. Entropic gravity proposes that gravity isn't a fundamental force at all, but an emergent phenomenon arising from the statistical behavior of microscopic degrees of freedom, similar to how temperature emerges from the motion of atoms. Each approach has supporters. Each has insights. None has emerged as clearly correct. The problem of quantum gravity remains unsolved. Why is this so hard? Part of the difficulty is practical. The scale at which quantum gravity effects become important, the Planck scale we mentioned earlier, is inconceivably small. For comparison, the Planck scale is to an atomic nucleus, as an atomic nucleus is to something 10 billion light-years across. We're nowhere close to being able to probe such scales directly, but part of the difficulty may be conceptual. Perhaps our entire way of thinking about space and time, the way Einstein taught us to think, needs to be replaced with something radically different. Perhaps space-time itself is not fundamental but emergent, arising from something deeper that we haven't yet imagined. Several approaches to quantum gravity suggest something like this, but no one knows for sure. Now, let me tell you about another deep puzzle that may be connected to all of this. It's called the hierarchy problem, and it concerns a simple but disturbing question. Why is gravity so incredibly weak? This might seem like a strange question. Gravity holds you to the Earth. It keeps planets in orbit and galaxies together. How can it be weak? But compared to the other fundamental forces, gravity is absurdly, almost comically weak. Here's a simple demonstration. Take a small refrigerator magnet and use it to pick up a paperclip from a table. Congratulations. You've just demonstrated that the electromagnetic force from that tiny magnet, something you could hold between two fingers, is stronger than the gravitational pull of the entire Earth on that paperclip. The entire planet. 6 trillion kilograms of rock, iron, and magma, all pulling down on that paperclip, and a small magnet overcomes it. Remember the comparison we made earlier? The electromagnetic force between two protons is about 10 to the 36 times stronger than the gravitational force between them. That disparity, that one followed by 36 zeros, isn't just a curiosity. It's one of the most unexplained numbers in all of physics. The strong nuclear force is even stronger than electromagnetism. Gravity stands alone, incomprehensibly weaker than everything else. Why? In physics, when we find numbers this extreme, we expect a reason. We expect some underlying principle that explains the disparity. But for gravity, we have no such explanation. It's one of the biggest unexplained numbers in all of physics. Some physicists have proposed that gravity only appears weak because most of its strength is hidden. In theories with extra dimensions, gravity might actually be just as strong as the other forces, but it spreads out into the extra dimensions, while the other forces are confined to our three-dimensional space. From our perspective, most of gravity's strength is invisible, leaking away into dimensions we can't access. This is an intriguing idea. But we have no evidence for extra dimensions. The hierarchy problem remains unexplained. And then there's dark energy. As we've seen, this mysterious component dominates the universe's energy budget, driving cosmic expansion to accelerate against gravity's pull. We introduced the problem earlier, but now let's confront just how bad it really is. The simplest explanation for dark energy is the cosmological constant, an energy inherent to empty space. Quantum mechanics tells us that empty space should have energy. Virtual particles constantly pop in and out of existence, and this quantum vacuum should contribute to the cosmological constant. When physicists calculate how much energy the quantum vacuum should contain, they get a number. When they compare it to the observed value of dark energy, the prediction is too large by a factor of 10 to the 120. That's 1 followed by 120 zeros. Let me be clear about what this means. This is the worst mismatch between theory and observation in the entire history of science. Nothing else comes close. Not by a factor of 2, not by a factor of 1,000,000, by a factor that dwarfs any number you've ever encountered. Something is terribly wrong with our understanding. Either our calculation of vacuum energy is completely mistaken, or something is cancelling it out to an extraordinary degree of precision, or our entire framework for thinking about these questions is flawed in a way we don't understand. This is called the cosmological constant problem, and it's been described as the worst theoretical prediction in physics. Many physicists believe that solving it will require a quantum theory of gravity. The cosmological constant problem sits right at the intersection of quantum mechanics and gravity, in the territory where our theories fail. Then there's dark matter. We call this something dark matter, and as we discussed, it outweighs ordinary matter by about 5 to 1. It doesn't emit light. It doesn't absorb light. It seems to interact with normal matter only through gravity. We know it's there because galaxies and clusters would fly apart without it. But what is it actually made of? We don't know. The leading hypothesis is some undiscovered particle, something beyond the standard model of particle physics. Many experiments have searched for such particles in underground laboratories, shielded from cosmic rays, hoping to catch a dark matter particle bumping into an ordinary atom. So far, nothing definitive. Other candidates include axions, very light particles originally proposed to solve a problem in particle physics, and primordial black holes that might have formed in the very early universe before stars existed. Some physicists have proposed that dark matter doesn't exist at all, and instead our theory of gravity needs modification at galactic scales. This approach, called modified Newtonian dynamics, or MOND, can explain some observations but struggles with others. The dark matter question remains open. Either our universe contains a vast amount of some unknown substance that we've never directly detected, or our understanding of gravity is flawed in ways we haven't fully figured out. Either option is humbling. What will it take to solve these mysteries? Perhaps new experiments will help. The Large Hadron Collider, the world's largest particle accelerator, has searched for evidence of extra dimensions, supersymmetric particles that might explain dark matter and other exotic phenomena. So far, nothing beyond the standard model of particle physics has been found. Future colliders, if they're built, might probe higher energies and reveal new physics. Gravitational wave astronomy is another avenue. LIGO and Virgo have already detected dozens of events, mostly black hole and neutron star mergers. Future detectors, both on Earth and in space, will be more sensitive and might reveal subtleties in gravitational wave signals that could test quantum gravity ideas. Observations of black holes continue to improve. The Event Horizon Telescope has imaged the shadows of supermassive black holes. Future observations might reveal deviations from general relativity predictions, hints of quantum gravity effects near the event horizon. Cosmological observations also constrain theories. Measurements of the cosmic microwave background, the large-scale structure of the universe, and the expansion history all provide data that any successful theory of quantum gravity must eventually explain. But honestly, the breakthrough might come from pure thought. Einstein developed general relativity primarily through theoretical reasoning, with minimal experimental input. He had the anomalous precession of Mercury and little else. The rest came from deep thinking about the nature of space and time. The next Einstein might be working right now on equations that will reveal what space-time truly is, how it behaves at quantum scales, why gravity is so weak, what dark matter and dark energy are, and what happens inside black holes. Or that person might not be born yet. Science is an open-ended endeavor. We never reach final answers, only better questions. The history of physics is a history of revolutionary ideas that overturned everything that came before, then were themselves overturned by the next revolution. Newton's gravity seemed complete until Einstein showed it was only an approximation. Einstein's gravity seems complete now, but we know it must be only an approximation too, because it contradicts quantum mechanics. Something deeper lies beneath, something we haven't yet glimpsed. This isn't a failure. This is how science works. Each generation stands on the shoulders of the previous one, seeing a little further, understanding a little more. The mysteries that remain aren't signs of weakness. They're invitations to the next breakthrough. Gravity is the oldest known force and the least understood. It's the one we feel every moment of our lives, the one that seems most familiar, most obvious, and yet it guards secrets that have resisted 3 centuries of investigation. Why does mass curve spacetime? We don't know. What is spacetime made of at the deepest level? We don't know. How does gravity behave when quantum effects matter? We don't know. Why is gravity so much weaker than other forces? We don't know. What is dark matter? What is dark energy? What happens inside black holes? What happened at the Big Bang? We don't know. We don't know. We don't know. But we're asking. We're investigating. We're thinking harder than humans have ever thought about these questions. And eventually, someone will find an answer. Maybe partial, maybe leading to even deeper questions, but an answer nonetheless. When that breakthrough comes, it will likely change everything. A true quantum theory of gravity wouldn't just be another theory. It might be the theory of everything, a unified description of all forces and all matter, a complete account of what the universe is and how it works. It might explain why the universe exists at all, or it might reveal that the universe is stranger than we ever imagined, requiring concepts we haven't invented yet, mathematics that hasn't been developed, ways of thinking that no human has ever had. The universe is under no obligation to be comprehensible to human minds. We evolved to survive on the African savanna, not to understand quantum gravity. And yet, remarkably, we've understood so much. We've traced the arc of cosmic history from the Big Bang to the present day. We've predicted the existence of black holes and detected them. We've measured the curvature of space-time and heard the ripples of gravitational waves. Whatever comes next, whatever theory eventually explains gravity at its deepest level, will be the product of human minds reaching beyond their evolutionary origins to grasp truths about reality itself. That's what makes this pursuit so profound. So the next time you feel your weight pressing you into your chair, or watch something fall, or look up at the moon hanging in the sky, remember what you're witnessing. You're seeing the effect of the deepest mystery in physics. You're watching space-time curve in response to mass. You're feeling a force that connects falling apples to colliding black holes, that links the formation of stars to the expansion of the cosmos, that shaped the universe and will determine its ultimate fate. Gravity is everywhere. Gravity is everything. And gravity is still waiting to be understood. The mystery is beautiful. The question is profound. And the answer, when it comes, will change how we see everything. Thank you for joining me on this exploration of gravity, the force we still don't completely understand. If you found this journey valuable, please consider liking and subscribing. It helps the channel continue making these deep explorations of science and the cosmos. Sleep well tonight, held gently to your bed by a force that has been shaping the universe for nearly 14 billion years, that curves the very fabric of space-time around you, and that remains, after all our centuries of investigation, profoundly, beautifully, wonderfully mysterious. Good night.